Homework 17, confidence intervals for population means, standard deviation known, video 5. I know the last example went kind of long because we were introducing the concept and simultaneously how to do it. I want to show you that the process is actually very streamlined and predictable. Let's take a look at this example where we are estimating SAT scores. A simple random sample of 100 freshmen has a mean math SAT score of 448. Calculate a 90% confidence interval for the mean math SAT score for all freshmen if sigma equals 115. The process is very straightforward. The first thing you have to do is make note of what your point estimate is. In other words, what is the mean for the sample? In this case, it's given to us, it's 448. If you're doing statistics with raw data that hasn't been processed, you have to calculate that first. Your second move is to find the critical value. And again, in my opinion, this is the hardest part, and it's not really that difficult, of constructing this confidence interval, because you have to understand what to do with the confidence level. The confidence level represents the center area under a standard normal distribution curve. So in this case, we want to cut off the middle 90% and figure out the z's that do that. Really, we only need one of them because we're going to do plus or minus later. They'll be the same except for their signs. The path from the confidence level to the z is pretty straightforward. The confidence level tells you the center area, but you need to know the remaining area of the two tails. Since the total area is 100%, the remaining area of the two tails is 10%, which means the area of each individual tail would just be 5%. But we're going to need to think of this as a decimal, so instead of writing 5%, I'm going to write 0.05. Kind of running out of room here. But because I'm going to be looking for this area inside of my z table, I need to write it with 4 decimal places. So we're going to look up an area of 0.0500, and that will tell us what the left z is. The right z will just be the positive version of it. If you have access to a z distribution table, and you should, we need to go find the row that contains 0.0500 or the number closest to it. So let me go to my z table, and remember that the areas are in order from left to right, top to bottom. So you just have to keep reading through it like a book. Well, on one side they're decreasing left to right for the negative z's, but they're in order from top to bottom, so you just have to keep going until you find what you're looking for. I'm looking for 0.0500, and I am looking in the negative 1.6 row. Now, in the negative 1.6 row of the z table, 0.0500 is not there. So I'm going to write the two numbers that it is between. It is between 0.0505, 0.0505, and the next area to the left of that is 0.0495. The 0.0505 is under the 0.04 column, and the 0.0495 is under the 0.05 column. So we have to decide which area to use. The area we're looking for is not only between these two, it is exactly in the middle. You can tell because if you ignore the decimals, this is 5 above 500 and this is 5 below 500. So which z-score should you use? Well, the rule of thumb is you go to the closest area, but if it's dead center, you have to make a decision. I know my decision, and I'm hoping it's consistent with the online homework. I'm going to find out here in a minute. But my decision when the area is dead center is to default to the one to the right because it will give you the larger z value. Why is that important? If we go slightly larger, we slightly increase the confidence level. If we use the lesser of the two, the z's move closer to the middle and we decrease the confidence level. You don't ever want to decrease the confidence level if you can avoid it. So when the area is dead center between two areas in the z chart, default to the one on the right. Our z is negative 1.65 on the left, positive 1.65 on the right. The hardest part is over. We have found the critical values, value and its opposite. Your third step is to calculate the standard error. Sigma sub x bar, which is sigma over the square root of n. Our sigma was 115. Our n was a very conveniently chosen 100. Convenient not only because I can square root it without a calculator, I can divide by that result without a calculator. This is 10. 115 divided by 10 is 11.5. Your fourth step is to calculate the margin of error. That is also easy. The margin of error is just the product of the critical value and the standard error. Or more simply, it's the product of the previous two answers. So 1.65 times 11.5. And if we multiply those with a calculator that's serving as a bookmark right now, 1.65 times 11.5, 18.975. That is the number that we will add and subtract to the point estimate from the first step to create our interval. So our last move is to calculate x bar plus or minus the margin of error. So our sample gave us a mean of 448. We will add and subtract the margin of error to that. And so our answer is the form from the answer to the subtraction problem to the answer to the addition problem. The subtraction problem has an answer of 429.025, and the addition problem has an answer of 466.975. And there's our confidence interval. We state with 90% confidence that the mean math SAT score for all freshmen at this school are between these two values. Now you're going to see me disappear off screen for a second because what we just worked out was one of the questions off of the homework. Now your question will probably have different numbers, but what I'm going to do to this four-part question is type in the answers to make sure everything's okay. Part 1 says make the 90% confidence interval round the answer to the nearest whole number. Okay, the 429.05 would round down to 429. The 466.975 would round up to 467. Please don't give me any trouble. Yay! The only reason I was concerned is because about my decision for the z to use the the 0.495 area, but it was a good decision. Part 2 doesn't ask us to recalculate things, but it asks us a question. If the sample size were 110 instead, would the margin of error be larger or smaller? In other words, if we bump this number up to 110, what would happen to the margin of error? Well, let's think about where the margin of error came from. The margin of error came from multiplying the critical value times the standard error. The critical value was independent of the sample size, so changing the sample size wouldn't change this. However, changing the sample size would affect the standard error. So let's think it through. What would happen to this fraction if I made this 100 larger? If the 100 were larger, then the answer to the square root of 100 would be larger, and we would have a fraction whose denominator just got bigger. What happens to a fraction when its denominator gets bigger? The fraction actually gets smaller. Think about cutting a pizza. If you cut it into 8 slices, but then you cut another one into 10 slices, did the slice get larger or smaller? It got smaller. So by raising the sample size, it lowers the standard error, which would lower this multiplication problem's product and lower the margin of error. So there's something to be said there, that increasing the sample size will actually lower the margin of error. So I'm going to fill in the drop-down menus. The margin of error would be smaller since an increase in the sample size will decrease the standard error. Check that real quick. Part 3. If the confidence level were 99.9% rather than 90%, would the margin of error be larger or smaller? So what these questions are basically getting at is, can you control the margin of error by adjusting certain values in the problem? In the first one, it said, what happens if we raise the sample size? And the answer is the margin of error got smaller because the standard error got smaller. But what if the confidence level got larger? If the confidence level got larger, think about what would happen to this middle area if we tried to cram more in there. It would force the critical values to move outward to get more area in the middle, and this z would be larger. If the z were larger, then when we calculate the margin of error, it would make it larger. So raising the confidence level also increases the margin of error. The margin of error would be larger since an increase in the confidence level will increase the critical value. And then the last question in this one, based on the confidence interval constructed in part A, so in other words, based on our answer there, is it likely that the mean mathematics score for the entering freshman class is less than 481? So let me say that again. This is what we're estimating to be the mean math SAT score for all incoming freshmen, somewhere in that interval. And the question was, based on that, is it likely that the mean mathematics SAT score is less than 481? Well, if we're 90% confident that the mean SAT score is in this interval, this entire interval is less than 481. So we're pretty confident that the mean SAT score would be less than 481. So in the drop-down menu, it is likely that the mean math SAT score is less than 481. The calculations are straightforward and predictable. Go get an X bar. I'll probably give it to you. Go find the critical values. That's going to take the most work. Stick the confidence level in the middle. Figure out the z's that cut them off by taking the remaining area, cutting it in half, and finding that area inside the z-chart. Calculate the standard error, that's a formula. Multiply these two answers to get the margin of error, and then add and subtract it to your X bar.